also the Big Bang, inflation phase, dark ages, star formation, the rise of dark matter, microwave background, objects, laws of nature, distances, light years, light, redshift, radiation, X-rays, cosmic rays, gravity, mass and weight, dark matter, neutrinos, life, extraterrestrials, SETI. So let's begin. I'm looking forward to it. Oh, we have more content, I'm sorry. Then we have stars and galaxies. Stars, celestial sphere, star names, star birth, small stars, giant stars, star brightness, HR diagram, binary and multiple stars, variable stars, exoplanets, novae, supernovae, neutron stars, pulsars, stellar clusters, nebulae, galaxies, the Milky Way, local group, quasars, black holes, event horizon. Then we have the solar system. The solar system, the sun, sunspots, solar eruptions, solar changes, planets, moons, years, day and night, solar calendar, atmosphere, water and ice, Mercury, exploring Mercury, Venus, visitors to Venus, Earth's formation, Earth's atmosphere, magnetosphere, auroras, the moon, lunar features, eclipses, moon probes, Mars, Martian moons, missions to Mars, asteroids, main asteroid belt, visiting asteroids, Jupiter, Jovian moons, Jupiter flybys, Saturn, moons of Saturn, Saturn's rings, Shepherd's moon, moons, I don't know what that is, Stating Saturn, Uranus, how rockets work, other propulsion satellites, how orbits work, types of orbits, space probes, pioneers, 10 and 11, Voyagers 1 and 2, space stations, Skylab, Mir, International Space Station, ISS, spacesuits, spacewalks, working in space, Apollo to the moon, one small step, 21st century moon exploration, rovers on Mars, missions to Mars, longest distance space travel, index and acknowledgements. So let's get to the juicy stuff. We're starting with the universe. It's got all sorts of stars here and galaxies. What is space? Space is the word used to describe everywhere that is not Earth and its surrounding layer of air, the atmosphere. The generally accepted point where the atmosphere fades to almost nothing and space begins is 100 kilometers above the Earth's surface. The region around our solar system is known as local space, while the space between the stars in our galaxy, the Milky Way, is known as an interstellar space beyond what is intergalactic space. Space is not an empty vacuum. It's a near vacuum called the interstellar medium. Each cubic kilometer contains a few drifting atoms of gas and dust, as well as many forms of energy. In the region of the Sun, this interstellar medium consists of about 75% hydrogen, 24% helium gas, and 1% dust. The interstellar dust consists of tiny grains of composite, mainly of silicitate, silicon, and oxygen, and graphite, carbon, as well as small amounts of iron. Between galaxies, the intergalactic medium consists mostly of ionized hydrogen, atoms of hydrogen gas, each of its single electrons striped away, so it consists of just one proton. Space is so enormous that common units of measurement such as miles and kilometers become meaningless, which is why people often use the word astronomical to describe exceptionally large numbers. And, here it is. In local space, distances are often measured in AU's astronomical units. One astronomical unit is the average distance between the Earth and the Sun. It's about 150 million kilometers, specifically 149,597,871 kilometers. Interstellar space. Distances are usually measured in light years. LY. 1 light year is the distance light travels in 1 year, about 9.5 trillion kilometers specifically. 1460730472580.8 kilometers. Some astronomers prefer to measure large distances in parsecs. PC. 1 parsec equals to 3.26 light years. A kiloparsec KPC is 1000 parsecs, and a megaparsec MPC is 1 million parsecs. This is the Andromeda galaxy that we see in the illustration. The nearest spiral galaxy in our own is here viewed across 780 kiloparsecs, about 2.5 suggest that there may be other universes that we can never know. The universe is everything that we can never know, all of space and all of time. Before the universe came into existence, there was nothingness, no space, no time, no energy, and no matter. The study of the universe, its history, future, and largest scale features is known as cosmology. Scientists believe that the universe started with an explosion known as the Big Bang. According to latest estimates, the universe is now about 3.8 billion years old. Since the Big Bang, the universe has been expanding and continues to do so. The most distant galaxies are moving away from us, about 90% of the speed of light. The universe was once thought to be everything that could ever exist, but recent theories suggest that our universe may be just one of countless bubbles of space-time. This computer image shows the general structure of the universe. The larger light spots are superclusters of galaxies linked by strings or filaments of smaller groups of galaxies. The darkest areas are vast tracts of thin gases and dust. The universe is getting bigger all the time as galaxies rush outwards in all directions. Although there is no maximum possible temperature in the universe, there is a very precise minimum possible temperature. The third law of thermodynamics states that it is possible for anything to be cooled to below zero, minus 273 degrees. Working in specialized laboratories, scientists have cooled substances to within a billionth of a degree of absolute zero, but they cannot achieve this ultimate low temperature. Matter is not distributed evenly throughout the universe. On the largest scale, the universe consists of thin filaments each one made up of millions of galaxies, each surround vast voids that contain nothing but clouds of intergalactic hydrogen. The largest structure yet identified is an extended line of galaxies known as Great Wall that isolated about 500 million light years from our galaxy. The size and shape of the universe. Over the centuries, there have been many proposals for the size and shape of the universe. Asian cultures had many theories about the universe. They often believed that Earth was its center. These historical ideas included the belief that the universe was a ball in the hand of a giant human. Another myth was that the universe emerged from a giant egg laid by a black-winged bird. One modern suggestion is that the universe has no measurable size and shape, that is, it's infinite and goes on forever in all directions. Other proposals for its shape include the irregular blob, a vast sphere ball, a flattish slab with rounded corners, and a giant donut-like torus. These images show three likely possible shapes for the universe. One is the flat universe. Although it looks thin, its top-bottom distance is many billions of kilometers. The ball shape is known as the closed universe. The saddle-like shape, which is this one, that kind of looks like a wave with the two sets of curves, is called the open universe. The universe has four dimensions called space-time, three of normal space, up, down, left, right, forward, backward, plus time. the observable universe is what we can detect and estimate from our observations and measurements. Using these estimates, the universe seems to be about 90 billion light years across, which is 150 million trillion kilometers. Did you know? Whatever its size and shape, it's known that the universe is expanding and that its speed of expansion is increasing. The multiverse proposal. People have long wondered whether the universe is part of something bigger, such as multiverse. Many universes believe side by side, one inside another, or even separate. Multiple flat universes may be stacked next to each other, as shown here. So we have this one, then this one, then this one, kind of like sheets of paper. Another possibility is that each may be inside the next larger one, or there may be one main universe with smaller ones embedded set into it. Other proposals include parallel universes, alternate universes, and those involving extra dimensions and additional realities. Some of these ideas are based on three-dimensional shapes that exist in daily life. One approach is to think that the universe we observe as being surrounded by another universe or even greater scale, and so on, becoming more enormous each time, like a series of spheres inside each other. Another proposal is to view our universe as one bubble, which is part of a multi-bubble system, with some bubbles shrinking or merging while others expand or divide into more bubbles. Some ideas involve the Hubble bubble, Hubble sphere, or volume. This is a huge bowl-shaped or spherical region. On its outside, space and its objects are racing away faster than the speed of light, so any light traveling towards the center of the bubble never gets there. Some multiverses are described in terms of mathematicians and have more dimensions than the usual three we can picture. Mathematical multiverses may have 7, 10, 11, or more dimensions. A further set of theories involve time progressing at different rates in different universes. This would mean that even if two universes start out much the same, they will evolve at varying rates and soon become different. The Big Bang. Events happened very quickly at the beginning of the universe. In order to explain what happened, scientists use measurement of time that are small as 1/10 million trillionth of a second. At first, the universe was indescribably small and hot. It had been getting larger and cooler ever since. In its initial state, the four fundamental forces, strong and weak nuclear forces, electromagnetism, and gravity, were unified into a single force. Gravity was the first of the four forces to separate, followed by a strong nuclear force. This triggered an event known as inflation, and the universe suddenly became billions of billions times bigger. About 1/1000th of a second after the Big Bang, the universe consisted of a dense sea of quarks and other particles. About 3 minutes after the Big Bang, there was a brief period of nucleosynthesis where quarks joined together to form neutrons and protons. For the first 300,000 years, the universe remained completely opaque. When it became cool enough for protons and neutrons to capture electrons and form atoms, the universe was now transparent. About 100 million years after the Big Bang, the universe stars began to shine. much to be discovered about the universe and the Big Bang. No one knows what the Big Bang looked like 3.8 million years ago, so it's usually shown as some kind of explosion. However, in its beginning, forces and matter were very different. Not even light, as we know it, existed, so no one knows what the Big Bang looked like. Scientists have recently proposed that there must be a fifth fundamental force known as dark energy or quintessence that prevents the universe from collapsing inwards under the force of its own gravity. The inflation phase. Cosmic or cosmological inflation is the very short amount of time immediately after the Big Bang, which happened around 3.8 billion years ago. The traditional explanation tells how the Big Bang happened to a tiny point which contained all the universe's matter and energy. That is called the initial singularity. The inflationary phase, when the universe grew at its fastest rate, is measured in a trillionth of a second immediately after the Big Bang. During this extremely short period, space may have been expanded to half the size we see now and the observable universe. This expansion happened incredibly fast at a speed which was faster than light. After the inflation, this speed was no longer possible. So we see here the Big Bang and how it expanded and it's expanding, and how the universe is still expanding. Here it says 1, it's the Big Bang, 2, the inflation, and 3, expansion occurs more smoothly. The inflation phase, when the universe suddenly expanded greatly, happened almost immediately after the Big Bang, in less than a fraction of a second. The fundamental forces of nature also come into being, with gravity emerging possibly as gravitational waves. There may have been early irregularities and inconsistencies in the ways that space, energy, forces, and time spread out, but if they did exist, these fluctuations flattened out so that space then spread out more evenly and smoothly. Temperatures also dropped during the inflationary phase from immersibly hot, perhaps 1,000 trillions degrees to 10,000 trillions degrees. Newer explanations about what happened after the Big Bang try to take the quantum theory into account, which applies that the tiniest scales of atoms and the particles that make them. Then we've got dark ages. And the page is black with white letters. The image taken by the Hubble Space Telescope shows galaxy UD-FY 38135539 near the furthest visible part of the universe, 13.1 billion light years away. It formed during the universe's reionization phase. The dark ages of the universe probably began 10 to 150 million years after the Big Bang. By this time, various forms of matter had come into existence. This matter consists of the particles inside atoms, such as protons and electrons. They has previously, I think that's a typo. They have previously existed together as whole atoms, but as the universe's heat energy grew, the particles separated and became free, known as ions. The Dark Ages began when energy cooled again and the particles began particles changed. Some atoms began to separate again, forming charged particles known as ionized plasma, a period known as reionization. I always struggle with the word. Also, during this time, the first stars began to form and shine. Gradually, the Dark Ages faded, probably between 500 and 1 million years ago. Evidence of the Dark Ages and early star formation comes from the furthest objects we can see. For example, galaxy MACS 0647 JD is 13.3 billion light years away, so we're seeing it in less than 5 million years after the Big Bang. Then we've got star formation. The stages in star formation have been worked out by cosmologists and other scientists. They continue to study the stars that are still throughout space. Clouds of hydrogen, other gases in space thus gradually clump together under their own gravity, drawing in more matter and becoming denser. Eventually, the matter becomes so hot and dense that the centers of nuclei of atoms begin to join or fuse. This nuclear fusion gives off light, heat, and other rays and energy. The star shines. This process probably first started to happen around 200 million years after the Big Bang. Before this, it was too hot and energetic for atoms to undergo nuclear fusion. This lone digital sky survey is a project to map and measure the distances of millions of galaxies, stars, and other objects from Earth. The survey is specialized to detect the feature called redshift. Combined with other evidence, this indicates the distance of a star or galaxy from Earth and the direction and speed at which it's moving. The SDSS, which is this Lone Digital Sky Survey, uses an optical reflecting telescope which mirrors 2.5 meters across, I think, the Apache Point Observatory in New Mexico in the US. The survey's results in effect look far back in time by detecting extremely distant stars, galaxies, quasars, and other objects. Light from the objects has taken billions of years to reach us. So to us now, they look like they did soon after the Big Bang. The SDS optical telescope is 2.5 meters across and has been collecting information since 2012. It will continue past 2020, which is this year. Hopefully it will continue in 2021 and so on. The rise of dark matter. In the 20th century, as cosmologists and astrophysicists learned more about the universe, questions began to arise. The overall structure, gravity, size, expansion rate, amount of energy, and other features of the universe could not be simply explained using ordinary matter of atoms and molecules. The idea of dark matter arose as an explanation. The theory that there must be something mysterious and unseen was first developed in the 1930s by astronomers such as John Oort, that was born suspicions grew further that in addition to ordinary matter and energy, there must be something else. Dark matter and its counterpart, dark energy, are so named because they are mysterious and so far under-detected. Today, dark matter and dark energy are assumed to exist by scientists, but in the timeline of the universe, when did dark matter itself arise? One proposal is the lambda-code dark matter model. This suggests that dark matter is made of extremely cold, slow, tiny particles that give out no light or other electromagnetic waves, which is why they are so difficult to find. These dark matter particles could have perhaps come into existence several thousand years after the Big Bang. Other calculations put the appearance of dark matter at tens of millions of years after the Big Bang. The galaxy cluster, this is the image. Abel 1689 contains more than 10,000 galaxies, 1,000 galaxies, which suggests it also has immense amount of dark matter, the gravity of which is affecting its expansion. Now we are at microwave background. The faint echoes of the Big Bang have been detected in the form of cosmic microwave background radiation that pervades the whole universe. Background radiation shows that the temperature of the Big Bang has now cooled about 2.7 degrees above absolute zero. American radio engineers Arno Penzias 1933 and Robert Wilson 1936 discovered the microwave background in 1965 while trying to find the source of radio noise that was interfering with communications. At one time, they thought the pigeon droppings on their antennae might be causing the interference, but after thorough cleaning, the noise remained. Eventually, they determined that the source of the noise was located beyond the Milky Way galaxy, and that the signal appeared to be coming from all directions. U.S. physicist George Gamow, 1904 to 1968, predicted the existence of microwave background radiation in 1947, although he believed it will be slightly warmer at around 10 degrees above absolute zero. In 1993, the first images of this radiation were produced by the Cosmic Background Explorer spacecraft, COBE, or SOBE. The COBE images show that the radiation was informed to within. Sorry, I didn't read the word right. The COBE images show that the radiation was uniform to within 1 part in 1,000 throughout the universe, with minute ripples showing areas that were fractionally warmer or cooler. A subsequent survey by instrument support, the WMAP satellite, has provided more accurate picture that shows how the distribution of temperature fluctuations in the background radiation exactly mirrors the large-scale structures of the universe. Slightly cooler regions were denser and contained the matter that eventually condensed into filaments of galaxies, while the slightly warmer regions became empty continuum of space-time, but most of the matter and energy is invisible to humans. Scientists now believe that the universe is made up of 68% of dark energy, 27% dark matter, and about 5% ordinary luminous matter that we can detect in the form of stars and galaxies. This bright galaxy is a single astronomical object, even though it contains billions of individual stars and is constantly forming new clusters of stars. The ordinary luminous matter is clumped together in objects of varying sizes and densities. The term object refers to individual items that astronomers can examine through telescopes. On Earth, matter exists naturally, mainly in three forms: gas, liquid, and solid. There is a fourth form of matter, a completely ionized gas known as plasma, that can be made in the laboratory and occurs rarely in nature, as in lightning. Beyond Earth's atmosphere, however, plasma, where atoms lose their electrons, is extremely common and is the main component of the wind produced by stars in the intergalactic medium. The largest commonly named astronomical objects are galaxies, followed in terms of diminishing size of nebulae, stars, planets, moons, asteroids, comets, and meteorites. Although galaxies are made of many billions of stars, they are considered to be single objects. This is because their stars orbit around a common center of gravity and have the same relative motion with respect to the rest of the universe. Astronomical objects tend towards a spherical shape because a sphere has balanced gravitational forces all over its surface. Objects of less than 200 to 400 kilometers in diameter, depend on what they are made of, have insufficient mass to achieve a spherical shape, which is why smaller asteroids all have irregular shapes. This size is known as the potato limit. Now we have laws of nature. Scientists can learn more about the universe by discovering the natural laws that govern the behavior of matter and energy and the relationships between them. William of Ockham, 1287 to 1347, an English philosopher, established that guiding principle behind natural laws. Known as Occam's razor, this principle states that hypotheses should not be multiplied without reason, meaning that the simplest explanation is likely to be correct. In addition to this law of universal gravitation, Isaac Newton, born in 1642 to 1727, also established the three laws of motion that govern the movement of all objects larger than an atom, unless they are moving at close to the speed of light. Albert Einstein, 1879-1955, developed a theory of relativity that extended Newton's law to include objects that are moving at near light speed. Einstein's theory of relativity led to his discovery of matter can be transformed into energy according to the famous equation E equals to mc squared, whereas E is energy, m is mass, and c is the speed of light. Albert Einstein discovered some of the mathematical laws that govern the relationship between time and space and energy and matter. most favorite theory, famous theory, but about something that has to do with his discovery of electro something. I don't remember what it is. I read it a long time ago, but I was surprised. I thought it was the theory of relativity. He never got a Nobel for that one. For mathematical equations devised the Scottish physicist James Clerk Maxwell, 1831 to 1879, described phenomena associated with electricity and magnetism and were used to predict the existence of the electromagnetic spectrum. In 1931, the Indian astronomer Subramanian Chandrasekhar, I'm sorry if I mispronounced the names wrong, born in 1910 to 1995, proved that no white dwarf star could have a mass of more than 1.4 times the mass of the Sun. Any stars that exceeded this mass will explode as supernova rather than shrink to become white dwarfs. According to Hubble's law, first stated by Edwin Hubble 1889 to 1953, in 1929, so many numbers, the speed at which the galaxy appears to be moving away from proportional to its distance away from us is proportional to its distance. The most distant galaxies are moving the fastest. English scientist Isaac Newton published his 3 laws of motion in the 1680s. They apply well to everyday situations, but Albert Einstein's law from the 90s to 1912s are more accurate for astronomical distances, speeds, and matter. Laws of motion. An object's Law 1. An object does not move unless something forces it to. In inertia, it will go on moving at the same speed and the same direction unless forced to change. That's the momentum. Law 2. The greater the mass of an object, the more force is needed to make it speed up, slow down, or change direction. Law 3. For every action, there is an equal opposite reaction. In other words, when something pushes off in one direction, the thing is pushing from is pushed back with equal force in the opposite direction. Now, let's see distances. The distance to the planets is measured by bouncing radar signals of them and timing how long the signals take to get there and back. The distance of nearby stars is calculated by measuring the slight shift in the angle of each star in comparison to faraway stars as the Earth orbits the Sun. This is called parallax shift. Parallax shift can only be used to measure nearby stars, so astronomers work out the distance to faraway stars and galaxies by comparing how bright they look and how bright they actually are. For middle distance stars, astronomers compare color with brightness using Hertzsprung-Russell HR diagram. This is called main sequence fitting. Beyond 3,000 light years, stars are too faint to main sequence fitting to work. I'm sorry, I was reading the above again and beyond 30,000 light years, stars are too faint for main sequence fitting to work. Distances to nearby galaxies can be estimated using standard candle stars that astronomers know the brightness of, such as supergiants and supernova. The expected brightness of a galaxy that is too far away to pick out its stars may be measured by the Thule-Fisher technique based on how fast galaxies spin. Did cameras with them, and they left them on the moon and only brought the films back because they didn't have enough weight on them to bring the cameras and moon rocks with them. So there are cameras on the moon that astronauts took them on the first mission. There's also a tiny sculpture by a German or Austrian artist there. He gave it to the astronauts, and our astronauts just left it there. So it's the only sculpture on the moon. And they also placed, I'm not sure when these were placed on the moon, four mirror-like objects that if you shoot a laser to them, it will bounce back in 1 point something seconds. Counting planetary nebulae. I don't know how to pronounce that. The rings of gas left behind by supernova explosions is another way to measure how bright a distant galaxy should be. A third method of calculating the brightness of a distant galaxy is to gauge how mottled it looks. Seen from Earth, the star is a constellation such as this part of a Big Dipper can appear to be of the same distance away. However, some may be much nearer than others. So this is the Alkaid Mizar Alioth